In the previous section, we handled FPGA FIFO overflow and underflow conditions. By the end of this module, you will be able to use FPGA FIFO methods to get number of elements and clear the FIFO. So on this slide, we see two additional methods that you can access using the FIFO method node. So first, let's talk about get number of elements to read. This one's going to return the number of elements remaining in your FIFO to be read. You can also use the get number of elements to write instead, and this one will return the number of empty elements remaining in the FIFO. So both of these are just two different ways of getting similar information, and you can use these methods to avoid underflow or overflow conditions by monitoring the status of the FIFO. So if you know how many elements are in that FIFO, you can maybe take some action to, if it's getting near overflow, maybe you can address that somehow. Okay, so one thing I want to bring up about FIFOs. So FIFOs retain data if the FPGA is stopped and restarted. Okay, so between stops and restarts, that FIFO is still going to retain its data. So usually that's not the behavior you want. Usually you want to start off with a empty FIFO when you're starting your FPGA VI. So if this is the case, then it would be good for you to use the clear method inside your FPGA VI. Okay, so when you use the clear method, it'll automatically or programmatically clear that FIFO. The way that you would get to the clear method is you would place down a FIFO method node, and then you can right click on it and then select method, control, and then clear. Okay, so at this point, if you're able to, go ahead and do exercise 8.1. And in this exercise, we will try to create an accelerometer threshold. And the way that we're going to do that is we're going to use some FIFOs and a lot of other different components. So for now, let me just demo the solution to you, and you can take a look at it. Okay, so I've opened up the solution for exercise 8.1. And if we look here, we've got a C-RIO that we're connected to right now, and we're going to create an FPGA VI for it. Okay, so one of the first things we do in this exercise is we create a target scope FIFO. In this case, we called it Y acceleration FIFO. And we're going to use this in our application. So now the FPGA VI is called accelerometer VI, which is right over here. So let's take a look at it. Okay. So let's go to the block diagram. So let's break this down real quick. So in the very first sequence, the first frame of the sequence structure, we're doing some initialization. So here we're setting some things to false. We're starting our module. We're specifying the data rate for our 9234 module. And then also notice here we're doing a FIFO clear. So because we expect that the FIFO is going to be clear at the beginning of this program, we're going to explicitly call the FIFO clear function to ensure that. Okay, now let's jump into the main code. So here we have an acquisition loop, and in the acquisition loop, what we're doing is we're reading the Y acceleration of a fan through a FPGA I/O node. Okay, the next thing we're going to do is we're going to take that data and we're going to write it to our FIFO. Okay. So we're putting that into the FIFO and we're going to read it out in the loop right underneath it. Okay, so we're going to write some data to the FIFO. We're also going to look at the timed out and monitor it and see if overflow occurred. If we happen to get an overflow, we're going to go ahead and stop our application and terminate it. Okay, so let's look at this bottom loop. So in the processing loop, we're going to read data out from our FIFO. Okay, so this has been transferred to the FIFO up here, and down here we're going to read elements from it. And notice that we're going to look at the timed out. So if this times out, that means the FIFO was empty. So if timed out equals true, we're just going to do nothing. Okay. However, if we read from the FIFO and it doesn't time out, that means we were able to grab some data from the FIFO. And in that case, we're going to take that data from element and we are going to display it on a indicator. And also we're going to do some processing with it. We're going to compare the current acceleration with the acceleration threshold. Okay, and if we see that the acceleration threshold is been exceeded by our acceleration, then we're going to display threshold exceeded as an indicator, and we're also going to write something to an FPGA LED. Okay, and then also we're going to monitor the terminate from up here. And if this has been terminated, then we're also going to terminate this loop down here. Okay. Lastly, we have a third loop here, and this is a loop that's controlling the speed of our fan. Okay, so here we have a fan speed control. Depending on how high that is, that's how fast our fan is going to be spinning. Okay, and we're also going to monitor the terminate control here as well. And then lastly, if we terminate, what we're going to do is we're going to make sure that we stop our FPGA I/O node, and we're also going to reset the fan speed to 0. So if something bad happens, we're just going to make the fan stop by setting it 0. Okay, so let's take a look at our front panel, and this has been compiled already. So I'm going to run this real quick. Notice that we're monitoring the acceleration of our fan. And right now we have a threshold here. So if it crosses this threshold, we want to know about it. Okay. The data rate we're going to acquire at is right over here. So let's start increasing the fan speed and see what happens. So it looks like, oh, well, now the threshold is starting to get exceeded. And if we keep making it higher, notice that the acceleration keeps getting exceeded. Okay. So it looks like our application is working, and looks like things are going pretty good because no overflow has occurred. And yeah, you just want to make sure you always monitor your overflow just so you know if you're missing some data possibly. So it looks like we are not missing any data here, and the program is running as expected. Okay, let's talk about some discussion questions. So why is it important to configure the FIFO data type to match the data that you will be writing to it? So this is important. You want to make sure that when you configure your FIFO, whatever data you're writing into it, you want it to match. Otherwise, there might be some coercion dots and you might have some unexpected behavior and it won't be as efficient. So in this case, the data type that we were putting into the FIFO was coming from our 9234 module. So what we should have done is we should look at the wire that's coming out of that particular module and see what the fixed point representation is. And when we create our FIFO, our target scope FIFO in the project, we want to make sure we make it a fixed point data type with the exact same configuration. Okay, so with the exact same sign encoding, word length, and integer word length. Second question, could this application have been developed using a VI-defined FIFO? In this case, yes. The reason why is because the FIFO is being only used on a single VI. So in that case, a VI-defined FIFO would have been fine. However, if we wanted to use sub-VIs to handle some of our FIFO functions, then we must use a target scope FIFO because that FIFO would have been shared between multiple VIs, namely the main VI or between sub-VIs. What is the purpose of the FIFO clear method in this exercise? So notice that in the very first frame we had a FIFO clear, and the reason we did that is because FIFOs will retain data between runs. In this case, for this application, we want to make sure that the FIFO is clear when we first start, so that's why we put a FIFO clear in that very first frame. Now you can use FPGA FIFO methods to get number of elements and clear the FIFO. Next, we will compare various FPGA data sharing methods.